spectral lines. So in the case of AM and DSB, you have two spectral lines, for each one spectral line in the baseband signal. Whereas also, if you have two signals, M1 of t and M2 of t, having different spectral lines, we are having a linear output of these two signals. Because if you say that M1 of t is having two spectral lines, M2 of t is having one spectral line, that means total input is having three spectral lines. Therefore, output of all these modulations may be giving you three spectral lines or six spectral lines, depending on type of modulation that we are going to have it. So that's why we say that amplitude modulation or all the variations of this amplitude modulation are of linear type. So all these modulations that we have seen, the amplitude modulation, DSPSC or SSB, gives you linear modulation. Now we will see another modulation wherein we are going to have the amplitude of the carrier is going to maintain constant value, right? After modulation, the carrier amplitude is going to maintain a constant value. Whereas in the case of amplitude modulation methods, the amplitude is going to change. Whereas here, we are going to say that the amplitude is going to maintain constant before modulation and after modulation also of your carrier signal, right? So what is the variation that we are going to have it? So we are going to have either frequency or phase variations, both combined. We are calling this as angle modulation. So because amplitude of your modulated signal is going to be constant, so if any additions are there or interferences are there, that can be observed and can be eliminated or reduced. Whereas in the case of amplitude modulation methods, if any interference comes, these variations cannot be reduced because your signal is going to be there, baseband signal is there in the amplitude variations. Therefore, if you reduce the interference, thinking that it is interference, that may be signal itself. So you can't vary the amplitude of the amplitude modulated signal to say that you are going to reduce the noise. Whereas in the case of the angular modulation, because the amplitude is constant, what are the variations in amplitude that can be nullified or reduced and say that the interference of the noise is reduced. So this is the advantage of angle modulation compared to that of your amplitude modulation. The noise performance of your frequency modulation is going to be better compared to that of your amplitude modulation. And this interference is going to be giving you a trade-off also between the bandwidth and the noise interference reduction that we are going to have it. Therefore, you can change the bandwidth of the signal so that the interferences can be reduced to the required extent. The bandwidth you can't provide, then you have to pay for that by going for more noise. Whereas if you can go for a more bandwidth, you can reduce the noise in the case of angle modulation technique. So these are the basic comparison between the amplitude modulation and that of your angle modulation that we are going to have. So we are going to have a detailed study about this angle modulation. So if you say that we have a signal AC cos omega Ct plus phi of t. So we say that when you change this frequency, this we said that it is the frequency modulation, and this change we call this as the phase modulation. Altogether, you can say that this is going to be the real part of e power j omega Ct plus phi t, right? Or we can say that this is something like e power j theta. Theta we are varying in accordance with our baseband signal variations. Therefore, this angle theta we are changing. That's why we call this as angle modulation. In this angle modulation, you have both frequency and phase variations that we are going to have it. So altogether, we call this as angle modulation. So if you say that theta equal to omega Ct only, that is phase is 0, then what we are having is AC cos omega Ct. So what does it mean? This AC cos omega Ct is nothing but the real part of this e power j theta with theta equal to omega Ct. What is e power j theta? It is a phasor with the amplitude and phase or the angle that we are going to have it. So as omega Ct changes, this will be moving as t changes. And if you say that we have this phi of c also a constant, the value of this theta at t equal to 0 is our phase phi of c that we are going to have it. So this is changing. Suppose if you say that the coordinate system also moves with the same angular velocity omega c, then what will happen? This phasor will be a constant. When you have a rectangular coordinate, fixed coordinates, this phasor is varying with omega Ct. But now what we are saying is this coordinate also is going to rotate with the same angular velocity. What will happen? This phasor will be a stationary one, like Earth is rotating, we are also rotating with the same speed, but we appear to be constant, but we are also moving as the Earth moves. Therefore, this is going to be a constant phase. Now on to this, we are having this phi of t, the phase variation that we are going to have it. That means depending on this phi of t or your baseband signal, this phasor will be moving up or down instead of being a constant. If there is no modulation, this is a constant phasor. If phi of t is changing, then this will be changing up and down depending on your baseband signal. So this is the variation that we are going to have it in the angle. That's why I call this as angle modulation. So if we have this theta it, which is changing linearly or monotonically, right? So this angle is changing linearly with respect to that of your input signal. So between T2 T plus delta T, if we have this variation, then this F delta T, the angular velocity of this will be equal to 1 by 2 pi theta I of T plus delta T minus theta I of T by delta T, the angular velocity. So this is the angular velocity with which your phasor is moving when this is moving monotonically. So between T2 T plus delta T. So you are having F delta T of T equal to the theta I of T plus delta T minus theta I of T by 2 pi delta T. That is the average variation in the signal that we are going to have it. The average angular velocity that we are going to have it is going to be given by this when theta it is going to change. So from this one we want to go for instantaneous frequency. What is instantaneous frequency at a particular time? What will happen if that be the case? This delta T should be tending to 0. So that means your Fi of T is limit delta T tending to 0 theta I of T plus delta T minus theta I of T by 2 pi delta T. So this is what the value that I got instantaneous frequency of the varying signal. So if we take out this 1 by 2 pi, what is the remaining thing? That is d theta it by dt, differential of theta it. Therefore, your Fi of t is it by the dt, the differential that we are going to have it. So this is the instantaneous frequency with which your phasor is moving when theta it is the phase variation that we are going to have it. So using this, we can represent theta it in a different form. Number of forms we can have it, and basically we will be having for two ways. One is correspond to your frequency modulation, and another one is correspond to your phase modulation. That means your baseband signal has to change this angle or angular velocity such that you are going to get the required variation. So if you say that your phase is going to be linearly varying with that of your baseband signal m of t, that is theta it equal to 2 pi fct plus kp into m of t. So m of t is 0, we are having your omega ct or 2 pi fct, that means the unmodulated carrier. When m of t is 0, no baseband signal, no modulation, therefore you are having theta it as 2 pi fct, the unmodulated carrier, and this we are having linearly increasing or decreasing depending on your m of t. So plus kp m of t. That is theta it is varying linearly with respect to our m of t, increasing or decreasing. That's what we are having, where Kp we are calling as the phase sensitivity. Kp is the phase sensitivity with the units radians per hertz, radians per volts. The Kp, the phase sensitivity, we are saying that phase angle we are measuring in the radians, right? So sensitivity we are saying as radians per volt. So Kp is radians per volt, and you are multiplying mt. So that means your mt should be in the voltage form. That's why we have said that mt is in the voltage. So what is the voltage signal that we are going to have it correspond to your input variations that we are going to have it. So whatever the physical signal that we are going to have it, convert that into a voltage equivalent. Then put into this so that you can get the required phase modulation, and that signal S of t is given as AC cos 2 pi FCT plus KPMT, because that is your theta IT. So your S of t is AC cos theta IT. Theta is varying linearly with your m of t with the phase sensitivity of Kp. So this is what your typical phase modulation equation that we are going to have it with 2 pi FCT plus KPMT. The other one is your frequency modulation. So frequency modulation will be having your instantaneous frequency Fc, Fit, we are changing as linearly proportional to your Mt. So Fit is Fc plus Kf into Mt. So when m of t is 0, you are having the frequency as Fc, the instantaneous carrier frequency, unmodulated carrier frequency. Then because we are talking about frequency modulation, we are saying that the frequency is linearly varying with Kf into Mt. Where Kf we are saying that it is the frequency sensitivity. Kp we said that it is phase sensitivity, and Kf is the frequency sensitivity. Because its frequency, the units are hertz per volt. And again, because it's hertz per volt, your m of t should be again a voltage waveform. And anyhow, the phi c, the constant we are taking as at both the places 0, so that we will be getting the required expression that we are going to have it. Therefore, theta it. So what will be your Fit is Fc plus Kf into Mt. If that be the value, the instant frequency or the angular velocity, then what will be theta it? When Fi is given, what will be theta it? The integral of this, because your theta it is, or Fit is 1 by 2 pi d theta it by dt. That's what we have seen previously. So we want to have theta it from your Fit. So that will be our integral of Fit dt. So we are going to get 2 pi FCT plus 2 pi Kf into 0 to t Mt dt, where Mt is your baseband signal or the modulate signal. Therefore, your Fm modulate signal St will be equal to AC cos 2 pi FCT plus 2 pi Kf into integral of 0 to t Mt dt. So what we are having is so this is your phase modulated signal, and your frequency modulated signal is cos 2 pi FCT plus 2 pi Kf 0 to t Mt dt. Right? So ST or VT, whatever you call the expression, that we are going to have it. The AM signal, the FM signal, and the PM signal, that we are going to have it. So these are the expressions for your phase modulated signal and frequency modulated signal. So how the waveforms will be looking like? The first waveform is your baseband signal, a single tone frequency, cos omega mt. The next one is the carrier, omega ct, which is a high frequency signal compared to your baseband signal. So when you modulate this, we are getting the amplitude modulation waveform is this, what we have seen already. Now for frequency modulation, your baseband signal m of t at the starting point is the maximum. That means when you have this maximum, this should be maximum. That means you should have a highest frequency component when you have the modulation signal as the maximum or the peak. That's why having a maximum variation in the frequency. Whereas when you have the negative peak, then you are having slow variation. Right? Similar to the phase modulation. If you look into these three, AM modulation, FM and PM, in the case of AM, the modulated output as it crosses 0, the spacing between zeros is the same, because your carrier frequency are not changing. The same carrier frequency is there, therefore 0 crossings remains the same. Only thing is, whatever the variation in the baseband signal has been referred in the envelope of your modulated signal. Whereas in the case of FM and PM, the 0 crossings are going to change because you are changing the carrier frequency also depending on your baseband signal m of t. When you have the m of t maximum at the phase modulation, you are having lesser durations. When you have m of t is negative peak, then the duration that we are going to have between the 0 crossings is maximum. So this is the variation that we are going to have it, and how the waveforms are going to look like in the case of AM, FM and PM, that we are going to have it. So here we are seeing that this is the phase modulated signal, and this is the frequency modulated signal, and both we are saying it is the modulated signals basically, right? Theta I2 we are changing, and they have the relation and similarities that we are going to have it, and obtain one modulated signal from the other modulated signal. That is, suppose if we have a frequency modulated signal modulator, this is the FM modulator, and we are having our m of t, and I want here a phase modulation. What is phase modulation? It is some constant into the baseband signal, whereas here we are having constant into integral of m of t dt. So instead of m of t, what if you put, you will be getting an expression like this. Instead of m of t, I want to have another circuit which changes this m of t. So what should be the m of t? Pardon? Yes, come on. Integral. So if you put integral, what will happen? Integral m of t you are getting, double integral you are going to get. So instead of integral, you say d by dt. So what is the output of this differentiator? D by dt of m of t. That is the input here. This is of m of t. So integral of d by dt. So both will cancel out. Only m of t you are going to get. Therefore, this is 2 pi k f into m of t. Some constant into m of t. That's what we want here. Constant into m of t. That means if you have a frequency modulator, if you want a phase modulated output, we can get it like this. Similarly, if you have an integrator and a phase modulator, we are going to get a frequency modulated output. This is integral 0 to t. That means here, instead of m of t, we are putting integral 0 to t m of t dt. So we are getting once again the required frequency modulated output. The same things I think I have given the slides also. Yeah. If we have integrated phase modulator, we are going to get the frequency modulated output. If we have a differentiator and frequency modulator, we are going to get a phase modulated output that we are going to have. This is the relation between your frequency modulation and phase modulation that we are going to have. In this frequency modulation and phase modulation, we will be having the words phase deviation and frequency deviation. Phase deviation and frequency deviation. What is the maximum phase variation that you can allow with the given m of t? That we call it as the phase deviation. And the maximum frequency variation that we are going to have it, in the case of carrier frequency, we call it as the frequency deviation. That is, you have this cos omega mt is your baseband signal, 2 pi fmt. So what will the value of this cos omega mt? It may take +1 or -1 the maximum. That means Fi of t can take a maximum value of Fc plus delta f or Fc minus delta f. Therefore, the maximum variation that you are going to have it is this delta f. From the center frequency, what is the maximum variation? We are not talking about the bandwidth. We are talking how much variation you are going to get from the center frequency. This is Fc, Fc plus delta f, Fc minus delta f. So this delta f is the maximum deviation. Similar in the phase, we call it as the phase deviation that we are going to have it. So how to get this phase variation of phase deviation and the frequency deviation that we are going to have it. For the time being, let us consider that a single tone modulated signal is available to us. That is, our m of t is am cos omega mt or am cos 2 pi fm mt, right? This is am cos mt. So for s of t for phase modulation will be equal to your AC cos omega ct plus AP am this is the unmodulated phase omega ct when mt is 0. Or your cos omega mt is 0, or this total am cos omega mt is 0, then we are having this is the unmodulated phase. And when this will be taking maximum, when this will be cos omega mt equal to 1. Therefore, the maximum deviation that we are going to have it is kp into am. This is what our delta phi, the phase deviation. And here, what is the value of this phase deviation? Kp into am. What is am? Amplitude of your baseband signal, and Kp is the sensitivity constant. So your phase deviation doesn't depend on your frequency. It depends only on the magnitude of your baseband signal. Your deviation does not depend on the frequency of your baseband signal. So you can change your deviation only by changing your amplitude of your baseband signal that we are going to have it. So this is one property that we are going to have it of your phase modulation, where it doesn't depend on the frequency of your baseband signal, or even on your carrier also. It only depends on the sensitivity and magnitude of your baseband signal. Whereas in the case of AM, you have the FC plus FM and FC minus FM. So your sidebands depend on your frequency, not on the amplitude. But here, the deviation is depending on your amplitude only. Then what will be the frequency deviation that we are going to have? Wait. So we are having our m of t equal to am or omega m of t. What will be our s of t for fm? equal to AC cos is the same omega CT plus 2 pi kf 0 to t am cos omega mt dt. This will be equal to AC cos omega CT plus 2 pi kf am and omega mt by omega m. Or this I will write as 2 pi Fm. This is 2 pi So this is the signal that we are going to have it. Where beta is going to be our phase deviation. This beta is the phase deviation of the FM signal, right? Omega CT plus beta sin omega mt. The maximization is beta. Or this is also called as the modulation index of your frequency modulation. We call this as modulation index or the phase deviation of your FM that we are going to have it. Therefore, here F by 3, that is delta F that we have got. Delta F, we have put it as Kp into Am, or if these two are equal, then this your delta F we are putting as Kf into Am and beta we are putting as delta f by fm. The modulation index that we are going to have it. So this is the relation between your modulation index and the phase, the frequency deviation. Beta is going to be delta f by fm that we are going to have it. So that is about your frequency deviation and that of your phase deviation. So this is the relation between your phase deviation and the frequency deviation that we are going to have it, or modulation index and the frequency deviation that we are going to have it. So from this one we will try to get the spectrum for our FM signal. What is the spectrum of your AM? A single tone frequency, two spectral lines. But what will happen here? This is our frequency modulated signal. So this is cos A plus B. Therefore, this will be equal to AC cos omega CT into cos beta sin omega MT minus AC sin omega CT into sin beta omega M of t. Cos A cos B minus sin A sin B. We are expanding this cos A plus B. So we have here cos of beta sin omega MT and sin of beta sin omega MT. So this cos of beta sin omega MT is a periodic signal. Therefore, we can expand this into a series, right? So instead of finding out the direct coefficients, this we are going to expand it in terms of your Bessel coefficients of order n. First order Bessel coefficients of order n. Therefore, this cos beta sin omega MT cos of theta, this is even function, right? This is cos of theta, even function. So what will be the coefficients? What are the characteristics of these coefficients of a even function? A periodic signal and even function. What will be the coefficients? All these coefficients will be of even. Whether if this is odd, sin of theta, you are going to have odd coefficients. Therefore, this will be equal to J naught beta plus 2J2 cos omega mt 2 omega mt plus 2 therefore theta cos 4 omega mt. And so on. Infinite terms. We are expanding this cos of theta in terms of Bessel coefficients. Then your sine beta sine omega mt will be equal to 2J1 beta sine omega m of t plus 2J3 beta sine 3 omega m of t and so on. These are the expressions of cos beta sine omega mt and sine beta sine omega mt. What is that we are doing? We are multiplying with this with cos omega ct. So when we multiply this with cos omega ct, what will happen? J naught be the cos omega ct. The first term that we are going to have it J2 beta cos 2 omega mt into cos omega ct. That is omega c minus 2 omega m and omega c plus 2 omega m. Similarly, this one omega c minus 4 omega m and omega c plus 4 omega m. So we are going to get all these expansion. So we are going to have the carrier frequency cos omega ct plus all the other harmonics of even functions 2 omega m, 4 omega m and so on. Sin omega c to sin a into sin b. So we are going to get sin omega mt into sin omega ct. So omega c plus omega m and omega c minus omega m. And this gives you omega c minus 3 omega m and omega c plus 3 omega m and so on. That means all these things with the cos omega ct, the carrier frequency and all the other harmonic frequencies with respect to our omega m, omega c plus or minus n omega m into c. So this is the signal that we are going to get, n varying from 1 to infinity plus or minus, that we are going to have it. So we have infinite frequencies. Maybe the amplitudes are different, J0, J1, J2, J3. The amplitudes goes down, no doubt, but we have infinite sideband frequencies. Therefore, theoretically, an FM signal requires infinite bandwidth. Theoretically, we want to have infinite bandwidth for 1 FM signal. But if you say that only 1 FM signal you are transmitting the entire bandwidth you are going to use, then no use. Therefore, we should have some restriction on this, how to get the required bandwidth for your FM signal. So here, so anyhow you multiply this and put all the sideband frequencies. We are going to get the different all the sideband frequencies with FC2 plus or minus positive and negative up to plus infinity and minus infinity, that we are going to have it. So all those things we are going to get. So if the modulation index beta is very small, then these coefficients of first order, zeroth order that we are going to have it, J naught beta equal to 1 minus beta by 2 whole square, and Jn beta equal to beta by 2 whole to the power of n if n is not equal to 0. This is for beta small. We can approximate the values of these Bessel coefficients J0, J1, J2 and so on. The sum of all these Bessel coefficients J0 square plus twice that of your Jn square is going to be half. So what does it mean? The maximum power that we are going to have it in the entire signal is AC square by 2 only. The power that we are going to have it in your moderate signal is going to be AC square by 2, because AC cos omega c, it is multiplied with all the signals that we are going to have it. So AC square by 2 we are going to get your signal PV equal to half. When we are talking about the audio signal, we said that if you can get more than 95 or 98% of the total energy of the signal, then we can restrict the bandwidth. So here, in the case of FM, we say that if it is going to more than 98% signal is going to pass the required number of sidebands, then we are going to get the required performance. Therefore, we are going to take that energy is going to be 98%. When beta equal to 1, we are going to consider J0, J1 and J2. Right? J1 and J2 we are considering. Then what is that PV that we are going to get? If you take from the Bessel tables, the value that we are going to get is 0.495. That means 99% energy is passed if you have these two sidebands J1 and J2. That means remaining all from J3 to infinity you can suppress without any disturbance that we are going to have, because we are going to get 99% of that. Typically, if you say that n we are taking beta plus 1, number of sidebands we are going to take it as beta plus 1. For all that, we are going to get 98% of energy. So if beta equal to 5, you take 6 sidebands. If beta is 11, you take n equal to 12. You are going to get 98% of the energy. That means the bandwidth that we require is that of twice that of beta plus 1, or n into Fm, and n equal to beta plus 1 into Fm. So therefore, the bandwidth required for your FM signal bandwidth B equal to twice beta plus 1 into Fm. Because n times Fm is the highest sideband we are going to take when beta value. N is beta plus 1, so beta plus 1 into Fm. So plus and minus, therefore bandwidth is equal to twice. Therefore, you are having the bandwidth is going to be twice that of beta plus 1 into Fm. But what is this beta? Beta we are getting as delta F by Fm. Therefore, twice delta F plus Fm. The bandwidth that we are going to allow is twice that of the frequency deviation plus the baseband signal frequency. This we call it as Carson's rule. To find the bandwidth of your FM signal. Carson's rule to find the bandwidth of your FM signal. Twice that of delta F plus Fm or twice that of beta plus 1 into Fm. So depending on the values that have been given, you can use the appropriate equation. So this is what the expression for the bandwidth of your FM signal. What is the bandwidth of AM? 2 FM. Whereas here we require 2 delta F extra. That's the deviation that we are getting. Okay, delta F is your deviation. So plus and minus bandwidth. So it requires more bandwidth compared to that of your AM signal. And theoretically it is going to be infinity that we are going to have it. But because of the energy restriction that we can place on that with 98% of the energy, we have got this as with bandwidth is going to be twice that of beta plus 1 into here we have got this value. This is what our FM modulated signal. Expanding your cos omega ct plus beta sin omega mt. Suppose beta is small compared to 1 radian. That is, your beta is less than 1 radian. When cos theta, theta is very small. What is the value of cos theta? Theta is very small. Cos theta is 1. And what is sin theta? It is theta. It is 0, 0 gone. Cos theta is 1 and sin theta is not 0. Sin theta is theta. Right? Therefore, this we will be writing as AC cos omega ct minus AC sin omega ct to omega mt beta. AC cos omega ct minus beta AC sin omega mt into sin omega Ct. One radian compared to our 1 radian. If beta is small, this is what we have got. Cos theta we have put as 1 and sin theta we have put as theta. So what is this signal that we are going to have it? This is AC cos omega Ct. And what will be the signal for our amplitude modulated signal? Cos omega Ct MAC cos omega Ct into cos omega mt. That is 1 plus m cos omega mt is in the bracket into cos omega Ct. So expand it. The carrier plus 2 side bands cos omega Ct into cos omega mt. And sin A into B. You are going to have cos A plus B minus cos A minus B. Okay? That means you are going to get again omega C plus omega m and omega C minus omega m. 2 side bands. You are going to get. One thing is magnitudes may be positive or negative. But when you take the magnitude spectrum, this and this will be the same. And they have the magnitudes. So we are having 2 FM as the bandwidth here. Similarly, this is also having 2 FM only. Compared to your 2 into beta plus 1 into FM, which is a wideband signal. Whereas when beta is small, we are getting the output of this signal is going to be narrow. That's why we call this as narrow band FM signal. Narrow band FM signal. Narrow band signal. The typical generation of this narrow band FM signal, the typical generation of this narrow band FM is we are having your modulating wave m of t, an integrator to give you sin omega mt, because m of t we are saying as cos omega mt, we are having sin omega mt, and we are generating a carrier of AC cos omega Ct. We are giving it to a 9 degrees phase shifter. It is not omega Ct plus 90, it is minus, so that we are going to get AC sin omega Ct. A phase shifter to give you sin omega Ct. So sin omega mt into sin omega Ct. So we are going to get the second term, omega Ct into sin omega mt, with some constants. Okay, that constant will be taken care with the AM and modulating signal. And some amplification also may be provided to get your required constants. And that we are adding here into the summation of your AC cos omega Ct. So this is AC cos omega CT. So AC cos omega CT is plus and sin omega mt into sin omega CT is minus. So the output of this summer will be a narrowband FM. This is what a typical of your narrowband FM. This will use it in the indirect method of generation of your wideband FM, because this will not transmit straight away the FM as FM signal, because it will not be having a constant amplitude, and harmonics also are going to be there in addition to your carrier signal. Therefore, this will use it to generate a wideband FM in what you call indirect method of generation of FM signal. So here we have got this as the AM signal and this as your FM signal. How the phasors will be? The phasors of this AM and FM can be shown like this. So we have omega C or AC. Upper frequency and lower side frequency. The upper side frequency FC plus FM, anti-clockwise direction, and this will be rotating in the clockwise direction. The carrier plus two side bands. So what will be the overall magnitude? This will be the increase. When this goes like this and like this, we are having only AC cos omega CT, because these two are going to cancel out. Side like this, the amplitude will be decreasing, right? AC into 1 plus m and AC into 1 minus m. So this will be 1 plus m and this will be 1 minus m. So amplitude is increasing and decreasing with this phasor diagram, right? That's what your phasor diagram of your AM signal. Phasor diagram of your AM signal. Then what is the phasor diagram of this? This is upper side frequency and this is lower side frequency. This is your AC and this is your resultant. At some angle theta or phi. Phasor diagram of your frequency modulated signal. The narrowband FM, not wideband FM, because wideband FM will be having all of the harmonics also. I have taken only omega c plus omega m and omega c minus omega m. Actually, in the case of Fm, we said that we want to have a constant amplitude. Right? The output of Fm output of the amplitude that we are going to get is the resultant of this carrier and these two side bands. Therefore, amplitude of your narrowband FM is not exactly constant. It is varying. And if it comes like this, it may be coming here and so on. Positive and negative. Resultant values, phasors that we are going to have to the different phase angles. Positive phase angle and negative phase angle. Maximum and minimum. So, your narrowband FM is not having a constant amplitude. Even though we are calling it FM, our narrowband FM is not of a constant amplitude. And not only that, you are going to have the third harmonic also in addition to our first harmonic Fc plus Fm and Fc minus Fm. The third harmonic also is going to be there in your signal. Therefore, this, as I said, we'll use it for generation of wideband FM in the indirect method of generation of your general FM signal, which we are calling as a wideband FM. Whether this is the narrowband FM signal. How your wideband FM becomes of constant amplitude. So this is one may be having number of phasors of beta plus 1 side bands. All these phasors, when they combine together, this will be giving you a constant. Right? When you have only one phasor, you are having resultant to be of different amplitude. But when you have this beta plus 1 phasors, you are going to add together to give you a wideband FM. Then you are going to get all those phasors combined together there, plus minus and so on, and depending on the values of Fc and Fm. So combined, we are going to get a constant amplitude wideband FM signal when beta is large. Right? So that is your phasor diagram for AM and phasor diagram of the FM signal that we are going to have, the narrowband FM. So that is the typical so when you say that wideband FM signal, beta we are saying it is large, right? So that your cos of beta sin omega cannot be equal to 1 now, because beta is large. So depending on the beta value, the cos theta value is going to change. Therefore, we are going to get different Bessel coefficients that we are going to get. So all those will be combined. That means you are going to get basically infinite number of sideband frequencies, J0, J1, J2, J3, Jn up to J infinity. We are having both multiplication with plus and minus n value that we are going. Therefore, we are going to get Fc plus F and Fc minus Fm and Fc plus or minus n times Fm that we are going to get. And because we are saying that 98% of the energy that we are going to get it, within that beta plus 1 as the order n, then we are going to get that many number of side bands is sufficient to give you the required signal without. So we'll be going for that one to give you a wideband FM signal that we are going to get. In the case of AM, we said that if you have M of t, M1 of t is having two spectral lines, M2 of t is having one spectral line. If you have a DSP signal, that output will be having 6 spectral lines. It is linear. But whereas in the case of the FM, when we have this multi-tone, let us say that we have 2 tones only, F1 of t and F2 of t, 2 baseband frequencies along with your carrier frequency of CT, and beta 1 is delta F1 by F1, and beta 2 is delta F by F2. The frequency deviation will be having the same for all the modulation that we are going to have it. And typical delta F that we are going to have it in the practical is 75 kilohertz. The practical delta F is 75 kilohertz. So the bandwidth is 2 delta F plus FM. So more than 150 kilohertz, and for each FM station we'll be having a bandwidth of 200 kilohertz. For each FM station we require a band signal of 200 kilohertz, whereas in the case of AM, each station is separate out in this frequency band as 10 kilohertz, because in the case of AM, your frequency starts 535 to 1640 kilohertz. Therefore, the first band or first station starts at 540. That means second station will be at 550, 560, 570 and so on. All those frequencies you can have as the carrier frequencies and have your AM signal. Whereas in the case of FM, we are going to have this bandwidth of each station is going to be 200 kilohertz. So this is our S of t with 2 tone frequencies F1 and F2, and beta 1 is delta F by F1 and beta 2 is delta F by F2. Therefore, this when you expand it as AC cos J and beta 1 and beta 2, the product, the cos of 2 pi Fc plus MF1 plus NF2. Cross products also are going to be there. Therefore, here in the output we are going to get Fc plus MF1, Fc plus NF1 and cross product NF2, and cross product of these two F1 and F2. So we are going to get MF1 plus or minus NF2 that we are going to have. That means now number of, if you say that for the F1 you are having beta 1 plus 1 side bands, and for F2 we are having beta 2 plus 1 side bands. We have our combine these two, the number of side bands live lobes that you are going to get it, sidelines are going to be much more, because you are going to have cos omega 1 into cos omega 2 also is going to be there along with your carrier frequency. Therefore, we have to have this multitone signal to have your other sideband signals also, not a linear combination of the signal. In the case of AM, we said that it is linear, but whereas this frequency modulation is not linear modulation, that's why you are going to have other combination frequencies also are coming into existence. They also will be giving you the required output altogether. Okay, so that's what your multitone frequency modulation with two frequencies that we are going to have it. So we said that in the case of AM, what is the maximum modulation index that is possible to have envelope detection or rectified detection? Maximum value of modulation index 1 or 100%. Okay, M we said that it is equal to 1. Whereas here beta we don't have any restriction that we have it. Beta depends on your relation between your frequency deviation and FM. So how much frequency deviation you want it, and what is the baseband frequency that we are going to have it. So if you say that your delta F is 75 kilohertz and FM is the maximum frequency, then what is the beta that you can allow? 75 by 15 equal to 5. But what is beta bandwidth that we are going to have it? 2 into beta plus 1 into FM. So this is 6, 15. That means you require 180 kilohertz. But typically we say that the deviation that we are going to have is requiring all the guard band and other things. Therefore, typically you have to restrict this to 150 kilohertz. Whereas, if you say that you are having beta equal to or FM equal to 5 kilohertz, then what will be the beta value? 75 by 5, 15. So 15 into this 5 into 2. Okay. So instead of 180 for lower frequencies, your beta is going to be giving you the required deviation. Or if you further reduce this frequency, because you are having up to 300 hertz, so you are going to have different beta values that we are going to have it, and based on that your bandwidth also is going to be changing. So if beta, if it is 0.1 or less than 1 radian, then we said that only 2 sidebands you are going to have it equal to that of your AM signal. AM is having 2 FM as a bandwidth, and your narrow band FM also is going to be having only 2 FM. Both are having the same magnitude spectrum that we are going to have it. Phases may be different, but magnitudes are the spectrum is going to be the same. When you take the VAFM of T and VFM of T for narrow band FM, both gives you the same value. Whereas if beta increases, the number of side lines increases and then your bandwidth increases. So we have to take care in generation of your FM also to have the required deviation to be obtained for all the band of frequencies from low frequency to high frequency that we are going to have it. Okay? So this is something about your frequency modulation and how the bandwidth is going to be there and how we are going to have the consideration for your Carson's rule that we are going to have it. Before going to the generation of this FM signal, we said that the bandwidth that we are decided by Carson's rule is using a single tone frequency. But we have the baseband signal as m of t. Consists of number of frequencies, the fundamental frequency and all the other harmonic frequencies that we are going to have it. A complex signal we are going to get. So what should be the bandwidth that we are going to have it for this type of signal? Most of the time we say that the signal is going to be of Gaussian distribution. Because when you say that, as per central limit theorem that we are going to study, circuits, whatever the input that we are going to give, the output of the final stage is going to be of Gaussian distribution. Therefore, most of the time when they are designing your circuit or approximating, we take the signal as a Gaussian distribution signal that we are going to have. So your baseband signal m of t is Gaussian. Therefore, the FM signal spectrum G of V also will be of a Gaussian distribution. Fc minus Fc is a square by 4 magnitude, and this will be the delta F RMS is going to be the variance of the distribution that we are going to have it. So your again probability theory course that we are going to have it, you are going to calculate you are going to get. This is the Gaussian distribution that we are going to have. So this total power in the signal, right? And to have the bandwidth consideration, we said that so taking that into consideration, this I'll write as 1 by root 2 pi delta F RMS F minus FC plus or minus. Let us put this as V by 2 minus this also. And this will be equal to 0.98. Not put the complete expression. You put this value also. So we want 98%. So in that one, you put this V by 2 pi delta F RMS equal to X, and this integral, and we have two equal spectral distributions that we are going to have it. So when you are having minus b by 2 to plus b by 2, you can say 0 to pi b by 2 with twice. Okay. Therefore, this I will put it as b by 2 yeah, we will be having this. Yeah. And this 2 pi also will not be there. And this is another function. And this we want it equal to 0.98. From the other function table, if you take for this value, for the particular b value that we are going to have it, then this into 1.4 delta. For this value of x of 1.64, you are going to get this equation to be satisfied as 98%, or this will be of 4.64 delta of. So this will be the bandwidth of required if the signal is going to be of a Gaussian distribution with a variance of delta FRMS, because we will not have a singleton this will be the bandwidth that we are going to have it of frequency modulated signal in terms of the Gaussian distribution that we are going to have. Okay. So that is about the frequency modulation, and what is the bandwidth, and how the spectral lines, and what is Carlson's rule, and what is going to be the wideband FM and narrowband FM. In the next class we will discuss about the generation of the frequency modulated signals that we are going to have. So as I said, that we are going to have a direct method of generation and an indirect method of generation, and afterwards we will see how to get back the original signal from this modulated signal, or how to demodulate the FM signal to get back our original M of t that we are going. Okay. Thank you.